So here's another indefinite integral. So we're looking for an antiderivative here. Your first hope, do you have a formula that lets you take the antiderivative of this? And you think back to some of your formulas, no, nothing really works. You could try to do a u substitution next. So if you let u equal what's under this root, your derivative of x squared minus 4 is going to be 2x, and I don't think your cancellation is going to work out very well, so it doesn't really seem like a u substitution, at least not the obvious one, is going to work. We could, I guess, write this as a product. We could write this as 1 over x squared times 1 over this square root and try to use integration by parts, but neither of those pieces is especially simple, so it doesn't really seem like that's a good option either. What you do notice here is you notice this root, and under that root you have a difference of squares. You have x squared minus 4. When you have a root that has a sum or difference of squares beneath it, what you can sometimes do to get rid of the root is perform a trigonometric substitution. And so if your root looks like this one does, where we have the variable squared written first and then minus the constant squared second, what you can try to do in order to get rid of the root and sometimes get to the point where you can find your antiderivative is you can attempt to let x equal a secant of theta. So if we try to do that here, this is what we're going to try to go with. We're going to try to let x equal a secant of theta. That should hopefully allow us to get rid of this root. And then maybe we'll get some cancellation to occur and we'll be staring at something a few steps down the road that we can actually find an antiderivative for. So we're going to let x equal, if this is a squared, right, we have an a squared sitting right here. A, I guess, would be 2, right? We squared 2 to get 4. So we'd be letting x equal 2 secant of theta. Now if we let x equal 2 secant of theta, what we're going to do with our integral, so I'm going to shoot the integral over here, and I'm just going to save the left side of my screen here to do some scratch work that'll help with all the substitutions that we're about to carry out. We want to figure out what to put in place of this dx, right? So the numerator within the integrand is still going to be a 1, but we want to change the variable of integration from x to theta. So what does dx equal in terms of theta? Well, you can take the derivative of x with respect to theta. The 2 is a constant, so we'll copy that into the derivative. And then the derivative of secant of theta is secant of theta tangent of theta. So what does dx equal? Well, right now it says dx d theta. I can multiply by d theta to figure out what I can replace the dx with. So dx is going to be 2 secant of theta tangent of theta d theta. So that's going to take the place of the dx. And that doesn't really seem like a good thing just yet, but hopefully whenever we figure out what goes on within this denominator, we're going to see some of these pieces are actually going to go away. We can put in place of the x right here 2 secant of theta, right? So we're going to have 2 secant of theta, and that's going to be squared, so I'm putting what I said I was going to let x equal right in place of this x, and then that's going to be squared. Now I am going to do a little bit of work over here with that root. Okay, the purpose of doing a trigonometric substitution is to really rationalize your expression, to get rid of the root. So if I was to do this substitution, x equals 2 secant of theta for this x, when I square 2 secant of theta, so I'd put 2 secant of theta here and then have to immediately square it, I'd get 4 secant squared of theta minus 4. Now, under a root, you can't really do the square root of this piece and then minus the square root of this piece. You have to have a factored expression under the root to do the root of the components beneath it. And so this now can have a GCF come out of it, right? 4 is a common factor to both of these terms. So when I factor out a 4, I'm left with secant squared of theta minus 1. Now that this is a product, I can do the square root of 4 and I can get a 2. Now if I put my root here and I put this same expression underneath it, I'm kind of in the same situation I was back here. I have a 2-term expression under a root, and that's usually an issue. There is a form of the Pythagorean identity that looks like this. I'm just going to try to fit this in up here. It says tangent squared of theta plus 1 equals secant squared of theta. So if you start with the familiar Pythagorean identity, sine squared plus cosine squared equals 1, if you divide everything in that by cosine squared, you've created this form of the Pythagorean identity. Well, how is this helpful? Check out what we have sitting here, secant squared theta minus 1. Subtract this 1 from secant squared theta, and your equation here says tangent squared theta equals secant squared theta minus the 1. So what can we replace secant squared theta with? Well, tangent squared theta. Now that's just a single term under the root. It is a perfect square, so what's the square root of it? Well, tangent of theta. So the root becomes 2 tangent of theta. So I'm just putting this expression, what the root simplifies to, in place of the root within the integrand. So we do have a little bit of simplification that happens right away, right? We can actually cancel this 2 with that 2. We can cancel this tangent with that tangent, right? And now we're going to have to figure out what happens with the rest of this stuff. So our integral is going to look like this. If I square this denominator here, or square this term within the denominator, this piece within the denominator, I'm going to have 4 secant squared theta. I'm going to factor the 1/4 out in front of the integral, right? This becomes a 4, it's in the denominator, factor it out as a 1/4. And then I have a secant squared of theta sitting in that denominator. I still have a secant of theta sitting over here. And I'm trying to do this integral with respect to theta. So if you cancel the secant of theta there with one of these secants from the denominator, your integral is going to be 1/4 1 over secant of theta with respect to theta. Doesn't really seem like we have an integration formula for that, but you know what secant is equivalent to, right? Secant of theta is equal to 1. I started this too far off to the side here. I'm not going to have enough room to fit it in. Secant of theta is equal to 1 over cosine of theta, right? So this can be rewritten right here as 1 divided by 1 over cosine of theta. Rather than dividing 1 by 1 over cosine, why don't I multiply 1 by the reciprocal of this? The reciprocal of this is cosine of theta over 1, or just plain old cosine of theta. So what this expression within the integral actually simplifies to is cosine of theta. We have an integration formula for that. So now we're in business. We're finally going to be able to develop an antiderivative here. Have this constant of 1/4. The antiderivative of cosine of theta is going to be sine of theta. It is an antiderivative, so we're going to have to tack on our plus c. Last order of business here is to make sure our result depends on the original variable, which was x, and not this new variable that we introduced, theta. So now we have to figure out how to get from this result back to a result that contains x's. If you go to this substitution right here, divide both sides of this equation by 2, and you have a line that says x over 2 equals secant of theta. This statement right here allows you to draw a right triangle. So I'm going to take some of my space over on the side here, draw myself a right triangle. I'm going to call that the angle theta. There's my right angle. What I can go ahead and do, based on this statement, x over 2 equals secant of theta, I can label some of the sides of this triangle, some of the lengths of these sides. Secant is 1 over cosine. Cosine is adjacent over hypotenuse. Secant, therefore, is going to be hypotenuse up top and adjacent in the bottom, right? Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. The reciprocal of that's going to have hypotenuse up top and adjacent in the bottom. So here's my angle theta on my triangle. I need to label my hypotenuse with an x. I need to label the side adjacent to the angle theta with a 2. If I know 2 of the 3 sides of a right triangle, Pythagorean theorem can get you the last. So if you apply the Pythagorean theorem to find the length of this leg, you're going to end up with x squared, the hypotenuse squared, minus the other leg squared under a root. And so now, how do we replace sine of theta based on this triangle? Well, you know sine of theta is going to be opposite over hypotenuse. So our result, dependent on x, is going to be 1/4. Opposite the angle theta, we have this root. So x squared minus 4, right? Opposite over hypotenuse, which is x. So I'm replacing sine of theta with opposite over hypotenuse from the triangle that this expression right here allowed us to draw. It is going to have a plus c on the end. I guess the last thing I could do, I'm not going to take another line to write this out. You know, this is multiplication of 2 fractions here, right? So I could just, in my denominator, have a 4x rather than the product of 2 separate fractions. But there is your result, trigonometric substitution.